Hello, and welcome to our video on Archimedes' principle.
So to start off with Archimedes himself, the creator of the principle was a man by the name of Archimedes. Archimedes was born in Syracuse, Italy. He became the most famous mathematician and inventor in ancient Greece. He was also very well known for his discovery of the relationship between the surface and volume of a sphere, along with its circumscribing cylinder. Throughout his life, he wrote many books, and in the first book of his work, On Floating Bodies, he proposed his principle, Archimedes' principle.
The buoyant force. The buoyant force is the force that an object experiences due to the pressure of the fluid. It is also important to note that the force acting up on the bottom of the immersed object due to pressure will be greater than the force acting down on the top of the immersed object due to pressure, which causes a net upwards force known as the buoyant force. There are three cases of the buoyant force. The first is when the buoyant force is greater than the downward force of weight. This causes the object to float. The second case is when the buoyant force and the force of weight of the object are equal. This means that the object will stay at the same level in the fluid, neither rising nor sinking. The last case would be when the force of weight of the object is greater than the buoyant force. This means that the object will sink in the fluid medium.
So to talk about Archimedes' principle, which is the basis of this video. Archimedes' principle is associated with the upward buoyant force on an object immersed in a fluid. The principle states that the buoyant force on an object is equal to the weight of the liquid or fluid that the object displaces. The buoyant force is a force that acts up on the center of mass of the object.
Alright, so here's an interesting practical application of Archimedes' principle. Well, it's that fish float with the help of the principle. To rise, fish release gas into their swim bladder, and since this increases their volume, and the volume of water which they displace, it must result in an increase in the buoyant force acting up on the fish. Because by the Archimedes principle, the buoyant force acting upward on the center of mass of an object is equal to the weight of the water that object displaces. To lower themselves, fish employ their swim bladder, decreasing their volume and the volume of the water they displace. This decreases the upward buoyant force acting on them, making them move downward.
So to talk about a real-world problem associated with Archimedes' principle. So a ship displaces 70 million liters of water when placed into the ocean for its maiden voyage. Find the upward force of the water on the hull of the ship.
The solution to the problem is as follows. It is very important to find the weight of the water displaced by the ship, because Archimedes' principle states that the buoyant force acting on the object is equal to the weight of water displaced by the object. In order to find the weight of the water, it is important to find the mass of water by using the density formula. The density of water is 1 kilogram by liter, and because 70 million liters of water are displaced, the mass of the water is 70 million kilograms. To find the weight of the water, use the formula for the force of the weight of water, which is equal to the mass of water multiplied by the gravitational constant of Earth, g, which is which is 9.8 meters per second squared. The weight of water is found to be 686 million newtons. Thus, due to Archimedes' principle, the weight of the water displaced is equal to the buoyant force. Thus, the buoyant force on the hull of the ship is 686 million newtons.
Okay, so let's derive Archimedes' principle using F1 and F2. So we can say that F1 is the force pressing downwards on the top of the box, and F2 is the force pressing upwards on the bottom of the box. To derive Archimedes' principle using F1 and F2, we have to understand that the force acting on a specific section of an object, like this one, is equal to the pressure acting on that specific section of the object multiplied by the area of that specific section of the object. We must also note that the pressure acting on a specific part of an object is equal to the density of the fluid that object is immersed in, multiplied by h, the distance from that section of the object to the surface of the fluid that object is immersed in, multiplied by g, the gravitational constant. Since both of these statements are true, we can say that the net buoyant, that F1 is equal to the density of the fluid the object is immersed in, multiplied by g, the gravitational constant, multiplied by h1, the distance from the surface of the water to the top of the object, multiplied by a, the area of the top of the object. We can also say that F2 is equal to the density of the fluid the object is immersed in, multiplied by g, the gravitational constant, multiplied by h2, the height from the surface of the water to the bottom of the object, multiplied by a, the area of the bottom of the object. Since this is true, we can say, before we do that, we have to understand that since F2 acts upward and F1 acts downward, the net buoyant force acting on the object must be equal to F2 minus F1. And since we know that this expression is equal to F1 and this expression is equal to F2, we can say that the net buoyant force is equal to this expression minus this expression. This means that the net buoyant force is equal to this entire expression, making this part of our solution true. So from here, we can factor out h2 minus h1. So if we factor out h2 minus h1, this means that the net buoyant force must be equal to the density of the object, multiplied by g, the gravitational constant, multiplied by the area, which is the same for both the bottom of the object and the top of the object, multiplied by h2 minus h1. And since h2 minus h1 is the same as the height of the object, we can say that the net buoyant force is equal to rho, the density of the fluid, multiplied by the gravitational constant, multiplied by the height of the object, multiplied by the area of the base of the object. So, since we know that the area of the base of the object multiplied by its height is the volume of the object, we can say that the net buoyant force acting on the object is equal to the density of the fluid the object is in, multiplied by the volume of the object, multiplied by g, the gravitational constant. Well, we also know that the volume of the object is equal to the volume of the water it displaces. And since we know that mass is equal to density times volume, and we have the density of the fluid and the volume of the fluid, we can say that the mass of the fluid multiplied by the gravitational constant is equal to the net buoyant force acting up on the object. So this concept is related to Newton's second law, which states that the force acting on an object is equal to the mass of the object multiplied by the object's acceleration. But in any case, we know that the mass of anything multiplied by g, the gravitational constant, is the weight of that thing. So we know that the net buoyant force acting on the object is equal to the mass of the fluid multiplied by g, the gravitational constant. And this means that the net buoyant force acting up on the object must be equal to the weight of the fluid displaced.
Okay, thank you. Okay, we're good.